Next we have number 18. In this one there are two multiplicative functions f and g, both of which are not identically 0. That means all of their values are not 0. And also they agree at the prime powers of prime numbers. So f of p to the power k equals g of p to the power k for each prime p and each positive integer k. Then we have to prove that these two functions are identical. The solution starts with the fact that both of them are multiplicative and both of them are not identically 0. Since f and g are multiplicative and are both not identically 0, so both of them have the value 1 when the input is 1. This is a property of multiplicative functions which are not identically 0 that we already proved when we were going through the results of this section. So at least f and g are the same, they behave exactly similarly in exactly the same manner when the input is 1. But we have to prove that they agree at every other positive integer also, so that is the next thing. So we consider any positive integer n greater than 1, and now we have to prove that f of n is equal to g of n. Now because n is greater than 1, we know from the fundamental theorem of arithmetic that n has a prime factorization, where the primes that you see, that is this pi's, p1, p2 up to pr, these are all distinct primes and the exponents ki are all positive integers. Now what do we know about f and g? That they agree at every prime power, where there is a prime and the exponent of course is a positive integer. So in particular for these prime powers appearing in this factorization also, that would be true. So now what shall we do? Let us see how we can calculate f of n. N is what? N is this product of prime powers and f is a multiplicative function. So you can write the f value of this as the product of the f values of the individual prime powers. Why? Because the prime powers themselves are pairwise relatively prime. When m and n are two positive integers and they are relatively prime, and if you have a multiplicative function f, you apply that on mn, that is you want to calculate f of mn by the definition of multiplicative function, that equals f of m times f of n. That's what you are doing here. It's extended version. You don't do it, you don't get it at once from the definition itself, but you apply that repeatedly. So first you think of this product as the product of two numbers. One of them is p1 to the power k1, the other one is the product of p2 to the power k2, p3 to the power k3 all the way up to pr to the power kr. These two numbers are relatively prime. So their f value is f of this times the f of the rest. And then you do that same thing to the second part. And once you go through such applications, finitely many of them, you ultimately get this product. But then you use this inequality, these equalities you use and get the corresponding g values of those same powers here. And then you kind of do a back calculation. Okay, so this product equals the g value of the product of the prime powers, which however is just n. So that way we see that besides having f of 1 equal to g of 1, f of anything else is also equal to g of that thing. That anything else of course is a positive integer. So the final conclusion is that f is equal to g, because f and g are matching everywhere. At every input they have the same precise output, and that is why they are the same. Next we have this number 20. Here we have a new function omega of n. For a positive integer n greater than 1, omega of n denotes the number of distinct prime divisors of n. When you factorize n, because this type of numbers have factorization by the fundamental theorem of arithmetic, the number of distinct primes that appear in that factorization, that number is omega of n. And along with that, omega of 1 has also been defined to be equal to 0. Actually, these two things could have been, this case could have been included in this one itself without mentioning this n greater than 1. Because if n is 1, then actually no prime divides n, because no prime divides 1, so the number of prime divisors would be 0. But for some reason the author has decided to show it separately. And here is an example also. For instance, omega of 360 is 3, because if you factorize 360, it equals 2 cube times 3 square times 5. So the primes that you see here are 2, 3 and 5. They are 3 in number. That's why we have 3 here. And this exercise has two parts. This is part A. We have to first of all show that 2 to the power omega of n is a multiplicative function. So let us first solve this and then we will see part B. To prove that this function is multiplicative, we have to take two relatively prime positive integers, say m and n, and then prove that the function value of mn, the product, is equal to the function value of m times the function value of n. So let us first of all dispose of the easy cases, and one easy case is this one, when m is equal to 1. M and n are both positive, but m can still be 1. So if m is 1, then this 2 to the power omega of mn is of course 2 to the power omega of n, and in place of this you can write 2 to the power 0 times 2 to the power omega of n, because 2 to the power 0 equals 1. And this 0 is actually equal to omega of n because of this, and because of the fact that m is 1. So we see that whatever we want, we are getting in this case. Similarly, there is another easy case, namely the case where n is 1. In that case also, this fact is true. Now, by similarly, you can actually go through the argument where you put n equal to 1 and go through a similar calculation, and you see that yes, it is true. Or what is more preferable is to understand, is to recognize the fact that this case itself implies this. Why? Well, that is because there is no special status of m. I mean, in this entire thing, I am not talking about the case m equal to 1, but I am talking about the general case. What we are calling m and what we are calling n, we can interchange their roles. That's what I am saying. So if we be really strict about everything, that we would really put whatever we have here in its proper place. Okay, so now I have proved this, that this is equal to this when m is 1, when the first number is 1. And now I want to prove this when the second number is 1. So what do you do? How do you use this case to prove this? You just write nm in place of mn, and then now your first number becomes 1. So you now use this. What will come? 2 to the power omega of n times 2 to the power omega of n. And in its place you can write this, because multiplication of real numbers is commutative. That's how this case follows from this one. And now we go to the general case where m and n are both different from 1. So next we have this case where m and n are both greater than 1. So each one will have a prime factorization. So this time prime divisors really are there. The omega values of these numbers are not 0. Both of them are non-zero. So let m have s number of prime divisors and let n have t number of prime divisors. Okay, where s and t are positive integers now. Then, since the GCD of m and n is 1, so the product of m and n will have s plus t prime divisors. How exactly? Let us see one small example. Suppose we take m equal to 6 and n equal to 35. We have taken a simple example. So So you know that the prime divisors of 6 are 2 and 3 because this is the prime factorization in fact. Similarly, the divisors of 35 are 5 and 7, prime divisors. And looking at the prime divisors, you can see that obviously they are relatively prime. Why? Because the only positive integer that divides both of them is 1. So that is also the greatest common divisor. Alright. Now Mn you can calculate is 210. What it actually is equal to that does not matter. What matters is that Mn is this. 2 times, 3 times, 5 times 7. So what are we getting here? The omega value of n is 2 because there are 2 prime divisors. The omega value of n is also 2 because there are 2 prime divisors 5 and 7. And the omega value of mn is 4 because it has 4 prime divisors. So the sets of prime divisors of relatively prime integers are disjoint sets. There is nothing common. So when you take their product, they come together and simply the number of prime divisors becomes the sum of the numbers of prime divisors. It is just that simple. So that is why obviously here the number of prime divisors of mn would be s plus t. There is nothing surprising about it now that we have seen this example. So then what are we going to get as a consequence? So in this case also we calculate 2 to the power omega of mn. Omega of mn is s plus t. So 2 to the power s plus t, which you can write as 2 to the power s times 2 to the power t, and which is just 2 to the power omega of m times 2 to the power omega of n. So in this case also we have got what we wanted to get, and that is why the given function 2 to the power omega of n is a multiplicative function. I am not writing that again here, okay, you can write the final line. Now before we leave this part A and go for part B, here is my question for you. Was it really necessary to consider those two first cases separately? Could we not have done everything at once? Just think about it, okay? But now we go for part B next. So this is part B. Here we have to establish a formula, an identity. For any positive integer n, we have to establish that the tau value of n square, the number of positive divisors of n square, not just prime divisors, okay, all positive divisors of n square equals this sum of 2 to the power omega of d, where d varies over the set of all positive divisors of n. So let's see how we can establish this. The formula, the given formula that you have to establish, it seems complicated for a general positive integer n, but luckily we can simplify our task. We don't have to even consider the general case. We instead observe this. Since both sides of the above formula are multiplicative functions of n, it's enough to prove the case n equal to p to the power k. Just that case where p is the prime and k is any positive integer. Okay, now comes the question of how exactly these are multiplicative functions. It's not very difficult to prove. In fact, it's an elementary task to prove that tau of n square is multiplicative, given that you already know that tau is multiplicative. Okay, so you can you can start showing that tau of n square is multiplicative the usual way. You take two positive integers m and n, which are relatively prime, and then you calculate tau of mn square. Let me just tell you what will happen. Tau of mn square means what? Tau of m square times n square. Because m and n are relatively prime, so are m square and n square. And tau is multiplicative. So tau of m square times n square is tau of m square times tau of n square. So there you have it. So the left hand side is a multiplicative function of n. The right hand side is, however, more complicated. But just now, freshly you have proved in part A that this function alone, this power of 2 as a function of d is a multiplicative function. So what you are seeing on the right hand side is a sum of a number of multiplicative functions, and the sum is such that d varies over the set of all positive integers, positive divisors of n. And now you go back and see the statement of theorem 6.4. Theorem 6.4 tells us that if we have such a sum, then as a function of n, this sum is also multiplicative. That's how this side is also multiplicative. Are these sides identically 0? Of course not. There are positive integers n for which both sides will be non-zero. So you can use the exercise 18 that we solved moments ago, and you can consider only this case. So by exercise 18, it's only enough to prove this formula true for this case. And let's now see how we can prove it in this specific case. Now everything has been actually drastically simplified. So we start with the complicated side of the formula, that is the right hand side in this case, where n is equal to p to the power k. Now this number is very simple in terms of having positive divisors. We know precisely what its positive divisors are instantly. The divisors themselves are powers of this prime p, and they are 1, p, p square, p cube, all the way up to p to the power k. So accordingly the sum looks like this: 2 to the power omega of 1 plus 2 to the power omega of p, and so on. Alright, now omega of 1 is 0. And what about the other omega values? These numbers, these powers of p where the exponents are positive integers, are divisible by only p, no other prime. So for each one of them the omega value is 1, and we have k such terms starting from omega of p and ending at omega of p to the power k. Besides this first one that is also there. So then let's continue our calculation. So what do we get from this? This is 1 and these are 2k number of 2's. So 1 plus 2k. And very nicely, that is just the tau value of p to the power 2k. Why? You recall the formula that we derived for the tau function. The number p to the power 2k has this itself as its prime factorization, in which only one prime is involved. So what do you do? When you have a general prime factorization, you add 1 to each exponent and then you take the product of those numbers. Here there is only one exponent, so you just add 1 to it and you get 1 plus 2k. So that way this value is 1 plus 2k. But what is p to the power 2k? P to the power 2k is the square of p to the power k. So are you not getting what you wanted to get? Yes. This sum equals the tau value of the square of this number. And by exercise 18, we then have the general case also. If you see, I have not written anywhere that exercise 18 is being used. I think you should do it when we were making that simplification in the first half of this solution. So there itself you write as the last line of that first paragraph. Hence it follows, where we wrote, it's enough to just consider the case n equal to p to the power k. In brackets you can write by exercise 18. So then you have your solution. And then of course there are other exercises also in this part, which we will solve next week. So see you next week with more exercises and their solutions. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.